third and final speaker is Michael DiNicola. He is a senior systems engineer in the Systems Modeling, Analysis, and Architectures group at the Jet Propulsion Laboratory. At JPL, Michael has worked on several mission concept developments and flight projects, including Europa Clipper, Europa Lander, and Mars Sample Return, developing probabilistic models to evaluate key mission requirements, including those related to planetary protection, and to infuse this modeling into trades throughout formulation of the mission concepts. He works closely with microbiologists in the Planetary Protection group to model assay and sterilization methods, and applies mathematical and statistical methods to improve planetary protection engineering practices at JPL and across NASA. At the same time, he also works with planetary scientists to characterize the plumes of, I can't say this word, Enceladus in support of future mission concepts. Michael earned his BS in math from UCLA and his MA in math from UCSD. Please join me in welcoming Michael DiNicola.
Hello, everybody. Can you hear me okay? Okay, great. There we go. Okay. Okay, so yeah, thank you for the introduction. I'm Mike DiNicola from the Jet Propulsion Laboratory. When I was introduced, this presentation will be on the planetary protection side of things. And so if you're not familiar with that, I'll just give a quick kind of brief on what that is. Giuseppe Cataldo, I think he presented from the MSR project yesterday in room C, I think, discussing kind of some planetary protection side of things for MSR, the Mars Sample Return mission. And what planetary protection is really is for the space missions that we do at JPL, there tend to be life detection aspects of those missions. And so we don't want to find ourselves in the situation of sending a spacecraft to another planet or moon and finding some biosignature of some kind and realizing it's because we sent something from Earth there and just discovered that. So that's one of the main motivations for the modeling we do in the planetary protection area at JPL. And so I'll take you through one example of that today. Really, what I'll be talking with you about today is not so much the design of experiments side of things, which you may have heard of on the last presentation, but more of how we, as maybe experimentalists, kind of bridge a gap to our modeling and use the observations from our modeling to make decisions in the end. So, clicker, right, here we go. I might have to be doing something right. Oh, jeez. Okay, got it. All right, thank you very much. Okay, so quick overview on what we'll be talking about today, where I'll be kind of demonstrating today is how Bayesian statistics and experimentation can be used to quantify uncertainty and what I'm going to call phenomenological models. I know it's kind of a mouthful there. It's kind of how we refer to models that are kind of physics-based, but sometimes we maybe don't understand the physics well enough to use a full kind of, F equals MA type model of the phenomenon. And so there might be some physics, but also some more experimental or empirically derived relationships that we use in the model. So when I say phenomenological model, that's kind of what I mean. Talk about how experiment and model can be brought together to determine risk in this case. And I'll discuss with you more about what do I mean by risk here. How modeling can help stakeholders make better risk-informed decisions and avoid unwarranted conservatism. So that's another aspect of things we'll touch on here. And we've in just my work at JPL, kind of noticed that when people don't know, or management stakeholders, things like that, don't know, and there's a lot of uncertainty, they tend to be very conservative. I think a very kind of human reaction to things, something that our modeling can help remove or alleviate some of that maybe unwarranted conservatism. And then we'll discuss some ramifications to the NASA Planetary Protection specifications, in particular as they pertain to sterilization. And I'll try and touch on a couple or a few missions in particular that were mentioned earlier: Europa Clipper lander and Mars sample return. Okay, so some background here. I'm going to start by just describing the chart on the right here, okay? And I'll go through the text in a moment, so don't feel like you have to read everything. What this chart is showing, though, is kind of where things were in the beginning before we did some more experimentation, before the modeling that I'm going to take you through was done. In the planetary protection area, they tend to think about how to handle contamination risk using a chart like this, where in this case, sometimes they'll bake out hardware or heat up hardware for certain amounts of time to kill off or sterilize those components or this entire spacecraft itself sometimes. And so this chart shows temperature on the horizontal axis and then a time at that temperature on the vertical axis. And then there are various curves on there from various manuals or specifications that say if you hold the hardware at, say, 200 degrees Celsius for about 100 seconds, then according to the blue dot specification, you'd reduce the bio load on the hardware by 4 orders of magnitude. Okay. And these are the kinds of charts that they've used in the past. So now I'm going to kind of switch over to the text on the side. So part of this, the work we were doing, they wanted to be able to talk about risk in terms of what's called a sterility assurance level. This is a kind of standard metric that's used in the medical industry and amongst the microbiologists. And they wanted to be able to use this metric in determining risk. So what that is the probability that the product, after being exposed to the sterilization process, is not sterile, essentially. So the sterility assurance level is of 1% would mean that there's only a probability of 1% that the hardware is not sterile, okay? Many times and in this case as well, the objective is to demonstrate a 10 to the minus 6th SAL, or sterility assurance level. So the probability of the product not being sterile after being exposed to a heat treatment, in this case, would be 1 in a million, okay? And so that's what we set out to do. And as you can see from the chart here, there's dotted curves on here extrapolating out where there was no specification, no data, things like that. And they wanted to kind of better inform themselves on those higher temperature parts of this chart here. And in particular, I'll point out, if you see on the right side of that chart, an X with a red box around it, that's in the NASA procedural requirements. These are documents that kind of are used on flight projects at NASA. That is the current sterilization requirement from heat, okay, which is 500 degrees Celsius for half a second. If you can demonstrate that your hardware will be exposed to that, then you can claim that it's been sterilized, okay? So what might be wrong here? And so that's what some of these pop-ups are pointing out. One, there's no uncertainty quantification on here. There's no clear way how to make credible predictions from a chart like this. There's very little, if any, experimental data that's available to validate some of this information on here. And how do we compare this with the SAL, a sterility assurance level? It's not really clear. And in particular, the X with the black square around it, the current NASA spec, has no real statistical interpretation. And we dug deep for a while and could not find any. Okay, so how can we kind of better that situation? And to do that, we developed an experiment, basically. And I'm not the person performing the experiments. I'm more of the statistics math person working with the microbiologists on this, but I'll give you a very kind of brief rundown of what that experiment was. They used what were called survival ratio experiments for the most part. There was also something called a fraction negative experiment used as a confirmation or validation of our results. I'm not going to get into that today. But the survivor ratio experiments, they essentially start with seeding a coupon with a number of what are called colony forming units. A certain spore bacteria is, and in this case, it was a very heat resistant bacteria known for being very heat resistant. About 10 to the sixth, or about 1 million of those are placed onto a steel coupon. Those are put onto this kind of steel plate that you can see in the picture here, and created a coupon holder. And that was then pushed under a heat lamp, essentially. And this heat lamp provided a rapid heating to being applied to these coupons that have been seeded with these microorganisms or this bacteria. And then after the heat exposure, these coupons are kind of pulled away from the heat lamp, allowed to cool for a minute, and then placed into an extraction fluid, and then the sonication happens, and extraction from the coupons is performed, and then they're placed into petri dishes that are then used to grow any surviving colony, we call them colony forming units, or any surviving bacteria will be put in this culture, and if it's still alive or viable, it will grow, and you'll be able to count them with your eye, the number that survived the heat treatment. Okay. So I've talked about fraction negative already. Okay. So some important, some notation I'm kind of setting up here as well, and I'll kind of point some things out here about these terms here. You'll see the R being the number recovered. So recovered from this heating process from the petri dishes after they've shown themselves to be able to grow still and remain viable. So we can actually observe that, okay? From the experiment, that's what we actually observe. Then on the other side here, this lowercase n, the number seeded onto a coupon, we perform control experiments to try and get a good understanding of how many are we actually putting onto these coupons that we're then putting under heat. The fact of the matter is we just really don't know. We have to do some controls to understand the uncertainty on those. And in our modeling, it's actually something that we predict. It's a predictive quantity. We don't actually observe the number of bacteria that we've placed on the coupon prior to heat treatment. We have to estimate it, and we do so with Bayesian probabilistic approach here. And the n sub s here, the number that have survived the heat treatment, well, that's what we're really interested in here. We can't directly observe that, though. We observe the survivors after they've been put through some extraction and growth processes after being exposed to heat, but we really don't observe directly the survivors, and it's something we have to essentially kind of in a way back into through our probabilistic model. Okay, this here on the left is a picture of the actual spores or bacteria that are placed onto these coupons. It's not the prettiest picture, but these oval micron size bacteria spores. So they kind of have a shield around them that keeps them safe from the elements, and it's particularly heat here. This is the strain here is ATCC 29669. This is the name of this kind of heat resistant microbe that we were testing here. And we would expose it to heat, different time temperature profiles, we call them. And that's what these curves are on the side here. You can see as the coupon is exposed to the heat lamp, you see the temperature going up rapidly and then dropping off, tapering off after we kind of pulled it out from under the heat lamp and it cooled. Okay, and the S of t here, a function, is what we call the survival function. Okay, it's a function of the temperature profile that we're exposing the microorganisms to. Okay, and then there's a term phi here. And so given that a spore has survived the heat exposure, what's the probability that it is extracted successfully from the coupon into the culture? Okay, that's the kind of latter part of the process that we're talking about after the exposure to heat before. And then there's a probability that there's a dilution series. I'm not going to go into this, but if you're in the microbiology area, there tends to be dilutions that are made to look at growth of the microorganisms. Not going to get into this in too much detail here, but we capture that part of the process as well in this. So the main thing to take away from here is that there's a number of spores that are placed onto a coupon, and it kind of looks like this here. And then there's a survival component to the model that we're really interested in. And then there's these other aspects to the model that are really a product of our experiment, because we need to extract these things and culture them. And we need to consider those effects when we look at our observations and analyze them. Okay, and a little bit more terminology here. The model you'll be seeing in a moment uses terms called D values and Z value. These are kind of microbiology terms again. A D value has to do with the amount of reduction, the log reduction of the survival fraction for microorganisms, and how much time it takes to reduce the survival the bacteria population by 1 order of magnitude. Okay. The Z value is how the change in temperature that's required in order to change that D value by an order of magnitude. You don't need to remember all this for what we're getting into. The main thing to take away from it is that if you know one D value, one point at which you can say, okay, my survival ratio will drop by an order of magnitude if I expose it to this temperature for a certain amount of time. If you know one of those, and then you know the Z value, you can put them together to assess survival at any other point in time on your temperature profile. Okay, that's the nice thing about these things. Okay, so 2 numbers that give us kind of all the information we need to assess survival here. Okay. Oh yeah, and one more thing. The model here, you can see these are simple models here, and that they're kind of they're linear in a log space here. They can be more elaborate. These are the models that we focused on for our work here. And one thing I'll note here is that the D value model, it assumes a property, what we call a memoryless property. Okay, what that means is that if the fact that a microorganism has survived up to a certain point of time in the time temperature profile, it doesn't really tell us anything about it surviving the next increment of time. That's an assumption of the model that we're using here. Okay, so it might, you can imagine cases where maybe you could think of a microorganism becoming more resilient, that the survivors up to a certain point might be more resilient after making it through, high temperatures up to a certain point in time. Here, we're assuming that, okay, that does not help us predict the probability that's going to survive the next portion of time. Okay, and this is actually a standard assumption made in a lot of these biological models, so we had some precedent for it here. Okay, so those D value and Z value graphs you saw a moment ago, we can write those as differential equations, and not too complex of differential equations here. The D value can be looked at in terms of both the D value and the Z value can be looked at in terms of constants here. The D value, which is the B sub t here, that the sub t there says, okay, that constant is going to change with whatever temperature you're at. Okay, and then in this kind of simple constant Z value model, the top differential equation is saying that your d value is going to change by a constant amount, that constant slope of the curve you were looking at on the previous slide. That differential equation describes that constant slope relationship. And then from here, we can actually, the nice thing about the simplicity of these differential equations is that we can solve them, and we end up with this kind of elaborate integral and exponentiation going on. But that, for computational reasons, that really helps us out a lot. And this S of t, our survival function, is a key element of our model here. We can evaluate that in the calculations in a relatively easy way. I wanted to note here, another way of doing this would be by using an Arrhenius model. This is something that might be more familiar to those in the chemistry area. We explored this a little bit, but we didn't do a full-up model for it yet. It's kind of an area of current research here. But if we went going down this road, we could start looking at things like activation energy and other things that would be, maybe more have some importance to the microbiology side for answering other questions. Again, that's future research, and the top portion here, this constant z-value model, is what we move forward with. Okay, so I mentioned earlier that how does our experimentation become a probabilistic model here, and how do we go from essentially differential equations that describe a phenomenon to a probability in the end? And so that's kind of stepping down this staircase here. We have phenomenological model, which we use differential equations to describe. We have we define a probabilistic model that generates the data. And I'm not going to get into this, I don't have time to get into this too much, but something called De Finetti's theorem is kind of a fundamental theorem in probability theory, where it uses the concept of exchangeability to essentially say that there exists some event out there that if you condition on it, you can treat your random variables, your events of interest, as independent of one another. So it's an existence proof for making, for one thing, an independence assumption. And then Bayes' theorem is used in how we calibrate our model with experimental data. So we have our model, now we get data, we calibrate that model with Bayes' theorem, essentially, Bayesian statistics. And then we make predictions from that model and using fancy integrals like below there, but essentially integrating over our posterior distribution and for various quantities of interest. For us, it's going to be that sterility assurance level, and that's what the math there described. What is our sterility assurance level when we integrate over all the possible d values and z values, the parameters of our model? So again, De Finetti's theorem, it provides us kind of this bridge from our phenomenological model, our differential equations, to a probabilistic architecture. And then Bayes' theorem allows us to calibrate with data in a way that updates as we get more and more experimental observation. And we get the De Finetti's theorem gives us this independence, this ability to assume independence once we have a valid conditioning event. And we have a binomial process here, which can then be assumed because we have independent outcomes happening, and with a survival probability of individual microorganisms surviving with this S of t function. And that allows us to write a probability model describing this process and go from those differential equations to something probabilistic. Okay, so now I'll just go through some output or our results from the modeling. The parameters of our model, this is one of the first things we look at from the Bayesian side of things. We had a d value and z value, or the primary parameters of interest. We also had a parameter having to do with the mean number of spores seeded onto the coupons in the beginning. But the focus was on the d value and z value parameters. And the Bayesian analysis allows us to look at interdependencies between these different things, which are important to capture in any model. And for those of you who are curious what kind of software was being used for this, STAN was used through the RStudio environment. If you're doing Bayesian analysis, highly recommend STAN to you. think it was mentioned earlier that it's hard to download. I say it's worth the time to learn how to download it. I'm going to stop there on this. If anyone has any questions on what the actual values mean here, D values and Z values, I can talk after. This is the primary result of the modeling here. This looks to me almost like looking at a side of the sun or some other planet, but it's a heat map essentially of time on the horizontal axis, exposure time to heat, and then temperature along the vertical axis. And there were two heat regimes and time regimes that we looked at here because of the different experiments that were done. I mentioned a survival fraction experiment that was done, and then these fraction negative experiments that I just briefly threw out there. Because there were two kinds of things going on, we had two different regimes of output. But we're essentially looking at different SALs here. And you can see on SAL, the sterility assurance level, the probability of the product not being sterile, okay? In the black area, that probability is about 1, so highly, highly likely that the thing is not sterilized. And then in the yellowish area is probability of about 0. We're talking like 10 to the raised to the negative 100 power, in the upper right corner. Very, very low probabilities of this product not being sterile, which is where we more want to be. And then there's this kind of cliff area here where things very quickly drop off. Once we, for a given temperature or for a given time, once we go beyond a certain point of exposure, the probability of the thing not being sterile just drops off very, very rapidly. Okay, orders of magnitude on that kind of blurry region. Got it. And this is just highlighting some of the specific curves from that chart there. In particular, at the beginning, if you remember, we were interested in a SAL of 10 to the minus 6, and that's being shown in that solid curve there. So we here we're essentially doing, able to say a lot more than remember what the current NASA spec was, 500 degrees C for half a second with no real statistical interpretation. Well, now we can provide a curve for reaching a SAL of 10 to the minus 6, and we can say, okay, if you give me a certain temperature, I can give you how much time at that temperature that you would need to be exposed to that heat for. Okay. And then just wrapping up here with some of the applications. So for Europa Clipper and Europa Lander missions, there were, I should say, Mars sample return and Europa Lander missions, onboard sterilization or direct in-flight sterilization is something that they've been looking at designing for. And having the 500 degrees C for half a second side of things was extremely conservative, making them kind of very much over-design their system for large mass increases because they were designing in-flight sterilization systems that would use an energetic material to heat certain boxes up, and trying to get to 500 degrees C was a much larger resource use of mass, and especially mass, than it would be to get to like 300 degrees C, which is what we were essentially showing. Okay, and then other applications would be indirect sterilization in flight. So sometimes there's a rocket motor, or Europa Lander, for instance, uses a rocket motor to slow down its horizontal velocity before landing on Europa in this case. And so we can start looking at taking credit for in-flight sterilization from the heating up of the solid rocket motor, okay? And this is just summarizing a lot of the points we've talked about already. In the interest of time, I think maybe we have 1, maybe 2 minutes left. Anyone has any questions, happy to take them. Otherwise, thank you very much.
Yes, we've got time for a question if anybody has anything. Again, I don't see anything online yet, but anybody in the audience?
Yes.
Very nice talk. So you had shown those SAL curves that show the resistance or the probability of survival for this heat-resistant spore. But what about extrapolating these results for like unknown spores that you may, see? How would you kind of account for that sort of uncertainty?
Yeah, very good question. So the way we handle, we didn't do any modeling of that, but that is a completely valid point. And the way, the direction they went here was to select a bacteria that was known to be one of the most heat resistant bacteria on Earth, and to use that as a reference and say, essentially, like, this bounds other what we think would be the the sow in this case for other organisms. But that's a important question to look more into, especially for missions like Mars sample return, where we're concerned about both contaminating Mars with Earth stuff, and so maybe this would be relevant to that, saying, okay, well, we want to make sure we don't that things are sterilized of Earth microorganisms when we send them to Mars, but Mars sample return is returning something to Earth, and so there's are there Martian life forms or cellular life of some kind or something, and would this curve apply to that kind of life that we really don't know? Well, that's a we can talk afterwards on that one. There's ways of starting to categorize it, but we have not captured that kind of uncertainty here. Yeah.
All right, let's thank our speakers one more time.